Let's study 9th standard ICSE chapter 7, reflection of light, part C, which is full of ray diagrams. First, let's understand what is a spherical mirror. We know what's a plane mirror, the looking glass at home. But a spherical mirror is imagined to be a part of a sphere. So, if you have any reflecting surface, which can be imagined to be a part of a bigger sphere, then such a reflecting surface is called a spherical mirror, which is of two types, concave and convex. Now here, this is a convex mirror because the inner surface is silvered. That is, there is a paint here to make it opaque, and now reflection can happen on the outer surface. Whereas if the outer surface is silvered and the inner surface is the reflecting surface, it is called concave mirror because it's shaped like a cave, the reflecting surface. A stainless steel spoon has both the mirrors, convex and concave. So before we start with the ray diagrams, we need to study certain definitions. The center of curvature. The center of the sphere of which the mirror is a part is called center of curvature. It's an imaginary point. Next, radius of curvature. The radius of the sphere of which the mirror is a part is called radius of curvature. Next we have the pole, which is the geometric center of the spherical mirror. So the actual mirror is from here to here. So geometrically the midpoint of this is out here. So that is called the pole. Next, the aperture. The plane surface of the mirror through which the light rays enter and fall on the mirror is called the aperture. For example, if this was an eye lens, which you will study in 10th standard biology, and this was the iris. Iris is the colored part of the eye. Sometimes it's brown, black, blue, and even green. It's made up of muscles, and there is a gap in between, a hole right in the center, a black hole, which is called the pupil. So this is the exposed part of the lens. The rays of light can enter through this hole, and they are blocked by the iris. So this is called the aperture. So again, the plane surface area of the mirror through which the light rays enter and fall on the mirror is called the aperture. Even in a camera, the opening of the camera through which light rays can enter in and fall on the lens, that opening, which can be shut with the shutter, so that opening is called the aperture. And the principal axis, it's the imaginary straight line which is passing through the pole and the center of curvature. Now if we randomly draw some ray of light from any angle on the mirror, let's say this is the principal axis, always draw the principal axis first, then draw the mirror. See, the ray of light is falling like this. Okay, it's not passing through the focus or the center of curvature, nothing like that. Then ideally what we do is, we take the center of curvature first and we draw the normal at the point of incidence. That's right. This line joining the point of incidence and the center of curvature is definitely perpendicular out here. It is the normal. And we know the law of reflection. Angle of incidence is equal to angle of reflection. So if this is the angle of incidence, then this will be the angle of reflection. So this way we can draw any diagram, but in our syllabus we won't have to draw such cases. We have some fixed cases, some 10 diagrams, ray diagrams which you have to learn. That's it. Let's understand what is the meaning of focus of a concave mirror and focus of a convex mirror. We have a concave mirror. Silvering is on the outside surface. This is the principal axis. Usually you draw two lines up and two lines down, such a big mirror. So if you have rays of light which are incident and parallel, so two rays are enough. In the textbook they have shown many rays, no need to show so many rays, two rays are enough. After reflection, they will meet at a point on the principal axis, and that is called the principal focus. Let me show the reflected rays with another color, just to make it very clear for you. This after reflection. Yeah. So now this is the definition of the focus of a concave mirror. It's a point on the principal axis where rays of light which were parallel and principal axis and incident on the concave mirror after reflection meet. They actually meet, and when they actually meet, the image is real. So it will be inverted, and you can see it's a point image, that is a very diminished image. So when you draw array diagrams, you can use these fixed measurements always. The center of curvature to focus is 3 centimeters, and focus to pole, let it be 3 centimeters. So the entire radius of curvature is 6 centimeters. That's the measurement I prefer. Of course, it's not compulsory, but if you stick to it, then consistently you will not make any mistakes. Also, in our ray diagrams, we should always have the rays coming from the left. Here I have drawn the rays from the right, but by convention, we always draw rays from the left. So the concave mirror won't be like this, it should have been drawn like this. But I just wanted to show you one case of what if we change it, it still works. The rules are same. Now let's draw a convex mirror. This time, the inner surface is silvered, principal axis, center of curvature and focus. This mirror's curved line, you can draw freehand, but it should look curved. No need to use a rounder, you can save your time there. Now rays of light parallel to the principal axis. So again, 2 lines are enough. In the textbook there are many lines which are not required really. Concave mirror is a converging mirror. Concave mirror is a converging mirror, and a convex mirror is a diverging mirror. That means after reflection they will diverge, they will not meet. But how do we draw the reflected rays? Well, use a ruler, join this point of incidence to the focus, that's right, to the focus, and connect them with dashed lines and just extend it. Similarly, just connect it with a ruler and just extend it. Remember, this should be entirely a straight line. It should not be crooked out here. So use ruler only and draw arrows everywhere. 1 arrow, 2 arrows, 3 arrows, 4 arrows. If any arrows are missing, you will lose marks. So you can see that they will never meet. They are diverging. But they appear to meet behind the mirror at the focus. They appear to meet. That means it's a virtual image. It's an upright image. And it's a diminished image. So that's the feature of a convex mirror. We can't take such an image on a screen. Only with our eyes we may see the image that is out here. So now we know how to define the principal focus of convex mirror also. When rays of light parallel to the principal axis are incident on the convex mirror after reflection, they appear to meet at a point on the principal axis, and that point is called the principal focus. So learn the definitions well, and if you understood the diagram, learning will become easy. Now here we have taken the rays of light parallel to the principal axis. What if they were parallel to each other but not to the principal axis? Then how would the image look? So first of all, concave mirror, silvering outside, principal focus. Let this be C, let this be F. So I'm going to use only 2 rays. Again, 2 rays are enough. 1, let it pass through F, and the other, let it be incident out at the pole. They could have been incident anywhere, but I've chosen these 2 rays. And imagine that they are coming from infinity, these rays. Of course, imagining infinity is insanity, but a faraway object like the sun will have rays of light coming like this. Now there are some rules which we need to remember. Whenever a ray of light is passing through the focus and incident on a concave mirror, after reflection it becomes parallel. That's right. And since the object is at infinity and it's a huge object like the sun, the image is going to be diminished. Not a point image, but a diminished image. It's a concave mirror, so it will be a real image. It will be an inverted image. So let me draw the image first here, because I know the image will be formed at F. The reflected ray with ruler, draw a parallel line. So we know what is the height of the image formed now. What about this ray? Well, obviously this will also meet. the other blue line at this point, because that's where the image is formed. And if you notice, here the angle of incidence and angle of reflection are equal. So it always obeys the laws of reflection. So, what is the nature of the image? It is real and it is upright. What is the location of the image? It is in the focal plane, that means at F. In the earlier diagram, we had drawn the image exactly a point image at the point F, but now it's not a point image. It has some size, although it's quite small compared to the sun. So the location is, it is in the focal plane. Plane just means a two-dimensional surface. For example, this board is a plane. Your paper is a plane, two-dimensional. Now, what about a similar diagram with convex mirror? Let's draw that. First of all, the principal axis, convex mirror, so the inner surface is silvered, pole, F and C. Now, if a ray of light is incident towards F, with a ruler, ensure that it was already passing through F. Then the rule for convex mirrors says that after reflection, it will become parallel. And the other ray, either I can draw it like this parallel to this black line here at the pole, or I can even draw a line here parallel to the black line, but assuming it to be passing from C. So let me try that now. With the ruler, ensure that it was passing through C. Because the rule says that if any ray of light is passing through C, or it is directed towards C, that is appears to be passing through C, appears to, because this mirror is opaque, this ray of light will never move to the right hand side, it will never pass through C, it only appears to pass through C. So, how will it be reflected? Well, it will bounce back. That's right, in such a case, always the reflected ray coincides with the incident ray, because what is the angle of incidence at this point? It's 0 degrees. This is the normal. Any line passing through C is the normal. So that's why it bounces back. So you can see, this is one reflected ray, this is the other reflected ray. They are diverging, of course, they will never meet, but it appears to meet out here. That is again in the focal plane. The reason why I am drawing a dash line here is because it's a virtual image. Here it was not required, a dash line. It's a real image, so a solid line is fine. And we should label it A dash, B dash. Here also, A dash, B dash. The B dash should always lie on the principal axis. It's a virtual image, so dash line is compulsory. All these dash lines, don't draw a solid line for virtual image. It's upright, virtual images are always upright. It's diminished. Convex mirror always gives diminished images. Always. There's no exception here. Convex mirrors always give virtual images, upright images and diminished images. Remember that. For concave mirrors, we have a lot of variety, which we'll talk about soon. So again, it's in the focal plane, that is a plane passing through the focus. Now the laws that I was talking about, I've already explained to you. Law number 1 for ray diagrams. If a ray of light is passing through C, or appears to be passing through C for both the mirrors, it will simply bounce back. That is, the reflected ray will retrace the path of the incident ray. For a concave mirror, how would it look? Something like this. It's a concave mirror. This is C. So it passes through C, so the reflected ray will be along the same direction. The second rule says that if a ray of light is parallel to the principal axis, then after reflection it will pass through focus. Even for a convex mirror, if a ray of light is incident parallel to the principal axis, then after reflection it will appear to pass through the focus. And the third rule, which we've already applied here, if a ray of light is already passing through focus, it will become parallel. If a ray of light is already appearing to pass through focus, it will become parallel. So keep these rules in mind. And of course we have the diagram at the pole as well. If the incident ray is incident at the pole, then it will be reflected such that the angle of incidence and angle of reflection are equal, and the principal axis acts like the normal here. Even here, if I would have drawn an incident ray at the pole, then this would be the reflected ray, and I would have been equal to R. So keeping these rules in mind, let's start with the ray diagrams. And whichever diagrams are double ticked in the pics which I have sent, you have to practice all these diagrams for homework. Concave mirror, it has some 7 cases totally. 7 cases, yeah. That means 7 ray diagrams. And we have to learn their nature of the image and size of the image and position of the image. But if you know the diagram, then knowing these things will be very easy. So first, for a concave mirror, what if the object is at infinity? We've already studied that. 2 rays from infinity parallel to the principal axis. They meet at F. Take care of the arrows, use ruler only. Show the silvering. What is the nature of the image? Highly diminished point image. At F, real and inverted. Second case is, again, object is very far away, almost at infinity. But this time the incident rays are not parallel to the principal axis, they are parallel to each other. So again, I've already drawn this diagram, I'm showing it again. So take 2 rays, let's say one is passing through F. So this will become parallel after reflection. And let's say the other one is passing through pole, incident at the pole. This is the reflected ray. Image, this one. Inverted image, real image, diminished image at F, that is in the focal plane. Next diagram. What if the object comes a little closer, but still beyond C, beyond the center of curvature? So this time I have to actually draw the object. So I like to draw the object 2 lines high. C, 6 centimeters away. Focus, 3 centimeters away. So we'll draw 2 rays. Let me use blue entirely now. 1 parallel. What happens to parallel lines? They pass to the focus after reflection for a concave mirror. Show the silvering, please. Second ray, let's take it passing through F. So what happens to that? It becomes parallel. So they are meeting out here. So here's the image. Arrows are very important. One on the incident ray, one on the reflected ray. So image is slightly smaller than the object. Image is inverted, it is real, and it is between C and F. On the same side as the object, not behind the mirror, in front of the mirror. Silver. Next case, what if the object is exactly at C, which is here. And notice how I said the radius of curvature is twice the focal length. Focal length is the distance between the focus and the pole, and the radius of curvature is the distance between the center of curvature and the pole. And it seems that the focal length is always half of the radius of curvature. That is why I told you to take this as 3 centimeters and this as 6 centimeters. Object at C, object between C and F, object at F. Let's see what happens in these scenarios. So, ray of light parallel will pass through focus, and ray of light passing through focus will become parallel. So where do they meet? Exactly at C. It has to meet exactly at C. Object size and image size is exactly same. Location at C, it's a real image. Same size, inverted image. Alright, now here. When the object was beyond C, the image was between C and F. And now when the object is between C and F, the image will be beyond C. So it's quite symmetrical here. Parallel will pass through F, and passing through F will become parallel. They meet out here. So for the first time, we are seeing a magnified image. And if you notice the various cases, as the object is coming closer to the mirror, the image is getting farther away and becoming bigger and bigger. So understand the gradual change in the ray diagrams. It's a real image, it's an inverted image. What if the object is at F? Now if you remember, when the object was at infinity, the image was at F. So now when the object is at F, the image will be at infinity. Again, symmetrical here. So ray of light parallel will pass through F. I can't draw a ray of light passing through F now. I have to use some other technique now. And I will join C and the head of this object. I will extend it. This will be my incident ray, and extend it backwards, which will be my reflected ray passing through C, of course. If you notice that both these rays are exactly parallel, they have to be exactly parallel. They should not be able to meet or appear to meet. Then only your diagram will be correct. So incident ray and the reflected ray are passing through the same line, and this was a rule, right? Whenever a ray of light is passing through C, it bounces back. So where is the image being formed? At infinity. It's a real image, it's an inverted image, and an enlarged image. Another way you can draw the second ray is, if you don't want to use C, you can make this incident at P, pole, and just draw a ray which appears to be parallel to this line. So even that is fine. And finally, the last case, the seventh case, what if the object is very close to the mirror? That is between F and P. A ray of light parallel will pass through F. Second ray, how do I draw the second ray? So again, let me use C here. So I just join C and the top of the object and make it incident on the mirror, and it just bounces back. Notice how they are diverging. For the first time, a concave mirror is diverging the rays. Usually it always converges and we get real images, but now a real image is not possible because these rays of light will never meet. But if you extend it behind, and please use ruler to make it extend, and don't tell me it did not fit on your page at all. Use the whole page, use double page, whatever it takes, but this has to be a completely straight line. It should not be crooked anywhere, and wherever it meets, then draw a straight line, and that's your virtual image. For the first time, we've got a virtual image for a concave mirror. It's an exceptional case. It's an enlarged image, it's an erect image, and it is behind the mirror. Let's label it as A dash, B dash. And for object, you have to write A, B in all diagrams. So don't forget A, B for the object and A dash, B dash for the image. All these things will fetch you full marks. So now you've understood all the cases, 7 cases of concave mirror. Now let's understand what happens for a convex mirror. In convex mirror, we just have 2 diagrams, that's it, fortunately. One is when the object is at infinity. That has 2 parts actually, so let's say there are 3 diagrams for convex mirror. Convex mirror, what if the object is at infinity and the rays of light are parallel to the principal axis? So they always show the silvering. That would prevent you from making silly mistakes. Here's F and here's the C. So it appears to be meeting at F, diverging rays. Convex mirror is a diverging mirror. But what if the object is far away and the rays of light are not parallel to the principal axis? Then we have drawn this diagram earlier actually. So one, let's assume it is passing through F. So it will become parallel to the principal axis. And the other, if you remember, I had drawn it passing through C. But just to show you a variation, this time I'm going to make a parallel line passing an incident at P. So reflected ray and reflected ray diverging. And where do they appear to meet? Here. At F. It should be an erect image. It's a diminished image. It's a virtual image. And the last diagram for convex mirror, so remember 7 plus 3, 10 ray diagrams. What if the object is anywhere else? You know, here, here, here. Well, we have only one ray diagram here because in all cases the nature of the image will be exactly the same. So let's draw it here. Ray of light, which is parallel, will appear to be passing through F or appear to be coming from F, and ray of light directed towards F, it will become parallel. If you draw a ray of light directed towards C, it will just bounce back. So which of these should I draw? Either will be okay, let me direct it towards C. So you will need a long ruler so that from here to here you have to draw a straight line, okay? It should be like this. Not crooked at all. Oh, it became crooked here. But you use a ruler and it just bounces back. So you can see the reflected rays are diverging. And where are they meeting? Out here. So that's your image. A dash, B dash, A, B. It's a virtual image, diminished image, erect image, behind the mirror, and between the mirror and F. That's the location of the image. So the next topic is uses of spherical mirrors. First of all, concave mirrors. They are very useful as a shaving mirror. If you remember, if an object is very close to the mirror, that is between F and P, what kind of an image do we get here? Can you recall? We get a magnified, erect, virtual image. So this will pass through F like this, and if this was C, and it appears to be meeting out here. Which case is this? The seventh case, isn't it? The image. So when you're shaving and you have a concave mirror, you get a magnified image of your chin or whatever part you're shaving. And it's erect. So it is very convenient to shave with a concave mirror. A plain mirror would give you the same size image. If you want a clean shave, convenient shave, then you use a concave mirror. Convex mirror would give you a diminished image. And if you keep yourself far away from a concave mirror, you'll get an inverted image. So that will be quite risky, because then instead of shaving your beard, you might end up shaving your head. So this give reason is important. And if they ask you to draw a ray diagram for this, then you know which one to draw. Next, as a reflector. Now in your textbook, it might be a little different, so study according to your textbook. But the concepts are the same. In a car, there's a concave mirror here in the headlights. So if I have a bulb at the focus, what happens is the rays of light, after reflection, they all become parallel. And you get a nice parallel beam of light which can travel a great distance. So that's how reflectors are used. And there's a diagram, figure 7.4, which is also double ticked. Whatever is double ticked, you have to practice them. Next, used as a dentist's head mirror. Now I doubt if this is exactly how it is presented in your book, but understand the logic anyway. A dentist, if you've noticed, or even a surgeon, wears some concave mirrors on their head. I'm not an artist, I'm a tutor. Concave mirror here, and we'll have some leaf on his head. Peacock feather, sorry, not leaf, peacock feather. Okay, this is a concave mirror, so when rays of light are incident on it, after reflection, they focus onto a point so that they can focus all the light onto your tonsils or onto your tooth where they want it to be focused, and then they can remove the right tooth or do the surgery. Next, convex mirror. First of all, as a reflector in street lamps. So imagine that the power supply in your building is gone, and your entire lane is gone, and you have your physics exam coming up next day morning. I'm sure that you are so committed that you will go out and study in the street lights. So how does it work? Well, in the street lights, you have this convex mirror. So here's the bulb. The rays of light will be diverged by the convex mirror. So a great area will be covered by the light. It won't be very bright light, it's a little diffused, but that's the whole aim of street lamps. Next, as a rear view mirror. Often you see the rear view mirror of your vehicle. It says that objects in the mirror appear to be closer than they actually are, and they appear to be small as well. So why do we use a rear view mirror? Why not a plane mirror? Well, because suppose this is a plane mirror, and here you are, here's your eye. So, and you're driving your vehicle. So rays of light from here will be able to enter your eye, and the rays of light from here will be able to enter your eye. So your field of vision is so much. So this is the wide range of things you can see behind you. You can see the bike on your sides, etc. But you can't see the bus at the extreme left or that person jaywalking on the extreme right. You would like to have a wider view of vision behind you. For that, we should use a convex rear view mirror, because if it is convex, then even these rays will reach your eye, and even these would. That means you get a wider range of vision using a convex mirror, which is what the whole aim was. So even this diagram is double ticked, so draw them. And finally, how will you distinguish between a plane mirror, concave mirror and convex mirror without touching them? If you could touch it, then checking out their shape and the bulging part, you can find out. But without touching, how can you be sure? Well, stand very close to the mirror. If you see that the image is of the same size as the object, that is your face is of the same size, that means it's a plane mirror. If the image is magnified and erect, it's a concave mirror. And if the image is diminished and erect, it is a convex mirror. So remember, for a concave mirror, when it's very close, it is magnified, like a shaving mirror. And for a convex mirror, it is highly diminished. Then we have differentiate between concave mirror and convex mirror, so learn the differences well. The solved examples, numericals are not in our syllabus anymore, so from 6th solved example onwards you can ignore it, but the first 5 solved examples, make sure you read them. It's not nothing to solve, but it is important from exam point of view, so please study the first 5 solved examples as well. Let's read the textbook now. Mark the definition of spherical mirror. Figure 7.20 is not important, you can cancel that. Now the difference between concave mirror and convex mirror is already explained. This is concave and this is convex. Certain definitions, terms like center of curvature, radius of curvature, these are all definitions. Pole, aperture and principal axis. So here, this is the center of the curvature, center of the imaginary sphere of which it is a part. Radius of curvature, pole, the geometric center, and the exposed part of the mirror is the aperture. Now remember that whenever a ray is incident on the concave or the convex surface, the reflection happens in such a way that the angle of incidence is equal to the angle of reflection. But for that we have to draw normal. Now normal to a curved surface is always drawn from the center of curvature. Even here, the normal will be drawn from center of curvature. Cancel this paragraph. You see, the radius of a circle is always perpendicular to the tangent at a point. That's the logic being used here to call it a normal. Now, definition of focus for a concave mirror, where they actually meet after reflection, the parallel rays, and here the parallel rays appear to meet or appear to be coming from. So that's a virtual focus. That's a definition of focus of convex mirror. So when you draw these diagrams, so many rays are not required, and even the normals are not required. Just 2 rays are enough. So double tick figure 7.25. This will also be the ray diagram when the object is at infinity. So for convex mirror we have 3 ray diagrams, out of which this is the first one. If the object is at infinity, the image is a point image, a virtual erect image at F behind the mirror. Focal plane is the plane passing through the focus. By plane we mean 2-dimensional surface, a slice of space. So when the object is very far away, not at infinity but very far away, then the image is again formed at F, but it has a height. This was a point image, this and this, but here we have a highly diminished image. For concave mirror it's inverted, and for convex mirror it is erect. Again, no need to draw so many ray diagrams, so many rays, just 2 rays are enough. So double tick this one and write here object at a far distance. For concave mirror, don't double tick yet, we have a better diagram later. Now there are 4 convenient rays for any ray diagram, out of which we use any 2. Cancel the theory part of it, but keep the pink boxes and the diagrams. Theory is cancelled, but the diagrams are there. When the incident ray is at P, that is a pole, the reflected rays is in such a way that the principal axis acts like the normal. Cancel this paragraph. Now we start with the ray diagrams. Theory is cancelled, but the characteristics have to be learned and the ray diagrams are double ticked. 31, 32, I've explained all this on board. 33, 34, 35, 36, and 37. So 7 ray diagrams for concave mirror. And inference is that as the object is coming closer, the image is going farther from the mirror and it's becoming bigger. And the last case is an exception because only in this case we have a virtual image. And a summary of all of this is seen in this table. Now for convex mirror, we'll have 3 diagrams. Cancel this first paragraph, double tick this, and this will be object in front of mirror. It could be anywhere, between F and P, at F, at C, between F and C, and beyond C. So we don't have different ray diagrams for convex mirror. We have only 3 ray diagrams, out of which 2 I've already marked earlier. And this is the third one. That's it. Cancel this paragraph. These are the characteristics of the image. So in the table, at focus the image if the object is at infinity, right here figure 7.25. At any other point, it will be figure 7.38. And there was one more figure 7.26 Bravo, for an object very far away but not at infinity. But that has not been included in this table, but you need to know it. Now remember that the focal length is always half of the radius of curvature. The derivation is cancelled. Proof is cancelled entirely. Now sign conventions. This is like any graph convention where right is positive, left is negative for x-axis, and for y-axis top is positive and bottom is negative. That's true for concave and convex. This will help us in numericals. So the theory part is just read. This is the lens formula. We'll be doing numericals with the help of this, where f is a focal length, u is object distance, and v is image distance from the mirror. Not lens. Lens is intense standard. Now we have a definition for magnification and a formula as well. It's a ratio of the image height upon object height, which is also equal to minus v upon u. Remember that if the magnitude, that is the value of the m magnification, is greater than 1, it's an enlarged image. If it is equal to 1, it is same size, and if it is less than 1, it is a diminished image. If it is positive value, that means it's an erect image, and if it's a negative value, then it's an inverted image. So the sign has a different meaning and the magnitude, that's the value, has a different meaning for magnification. U will always be negative for any mirror because object is always on the left. V will be negative for real images and positive for virtual images because only in virtual images is the image on the right hand side, that is behind the mirror. F is positive for convex mirror but negative for concave mirror. Uses of spherical mirrors: shaving mirror, mark it as a GR. We use concave mirror because if we are very close to the concave mirror, if our face is very close to it, we will get a virtual image, erect image, and magnified image. So we can see each and every strand of hair clearly, shave properly. It's important that it should be an erect image because if it is inverted, then we might shave off our head accidentally. As a reflector, often you may have seen reflectors or headlight or automobiles. That's how a reflector looks. Imagine this is a car, here's a bulb, you get a parallel beam reaching far and wide. A doctor's head mirror also acts like that. These are all GRs. Convex mirror is used for street lamps because it's a diverging mirror, so more area will be covered. Even rear view mirror, you can see that a plane mirror gives you a smaller field of view, but a convex mirror, rear view mirror, will give you a larger field of view. So that makes driving safer. Highlight the words wider field of view. Distinction between plane mirror, concave mirror, and convex mirror without touching it. So you cannot know the curvature. So how will you know? Well, if you're standing very close to the mirror, if the image is of same size, it's plane. If it's diminished, it's convex because convex mirror can only produce diminished images. That's it. No exceptions. And if it's enlarged, it's a concave mirror. Differentiate between here. Add a fifth point. It has a real focus. It has a virtual focus. Hi students, this is AJ sir. If you like this video, press the like button. If you would like to enroll for my online test series or online lectures, email me or message me on Instagram. Check the description for more information.